basic topic of diodes. I hope all of you have studied diodes in your class 12th or class 11th in your electrical subject, that is in the physics, in the subject of physics. So mostly, as I had seen in the last semester also, that when I was taking the classes for the P and the Q group, then most of you were aware of the diode and its characteristic. So if you look at this figure, what are the different things can you see? My question is that, are you aware of all this, all that is shown here? Whatever is
Yes,
shown in
sir.
this figure, are you aware of all these things?
Yes, sir.
Yes, sir.
Okay. So what do you see in this figure? First of all, there is a figure A in which you can see two regions. One is called the P region, other is called the N region. And then you can see there are certain minus signs on the P side, which is circles with minus sign on the P side, and there are positive signs on the N side. What are these minus signs on the P side?
Mobile
Electrons.
The minus sign on the P side, what are these things?
immobile
Majority
Sir,
of
electrons,
carriers.
sir.
Minority charge carriers.
Electrons.
Electrons. Anybody else?
Immobile charge.
Yeah, it is the immobile ions. Okay, it is the immobile charges over there, which are shown by the negative sign with a circle. Similarly, on the N side, you are having plus sign within a circle, and they indicate positive ions. Okay, positive ions. Then in the center, what you see, there is a certain plus and minus signs accumulated together, and that is called the depletion region. What does a depletion region mean? Why is it called a depletion region?
It won't allow charge to flow.
It doesn't allow charge to flow.
Sir, because it's a junction barrier, sir.
It's a junction barrier. But why is it called depletion region?
Sir, maybe it depletes the voltage.
It depletes the voltage? No,
Or current.
no.
Sir, in depletion layer,
Yeah.
Carriers.
Huh? So on the P side, if you see, there are certain spherical gray colored spheres. Okay, small balls of gray colored are there. Gray color are there. So what are these?
Hole.
Oh yeah.
Holes.
Okay. So these
Holes.
are holes. These are holes. Okay. Similarly, on the N side, hello. हाँ नहीं मेरे को रिप्लाई नहीं उसमें क्या कर देना है क्या देंगे कुछ भी मेल कर देंगे थोड़े बन जाएगा मेरा भी क्लास चल रहा है बाद में करता हूँ hello okay
Yes, sir.
so on the inside you can see there are minus signs okay so these are what
Electrons.
yes these are electrons and along with that you can see that there is a certain there's spherical there are spheres also gray colored spheres on the inside also. And what are these gray colored spheres that you can see? There are just two spheres.
Holes.
Minority charge
holes,
carriers.
Minority. Yes, minority there.
These are the holes on the N side. Okay, holes present on the N side. Similarly, you can see on the P side, there are certain negative signs which are not encircled. Okay. There are two such signs you can see. So again, these are called as the minority charges on the p side. Okay, these are the minority charges on the p side. Yeah. So in this whole figure number A, you can see that on the p side there are holes which are in a large quantity, and there are some electrons also on the p side which are in a small quantity. So these holes which are in large quantity are called as majority charges on the p side, and the electrons which are less in number on the p side, these are called as the minority charges. So on the p side, you are having two kind of charges. One is the majority charge, other is the minority charge. Okay. The same thing follows on the n side, that on the n side the majority charges are the electrons and the minority charges are the holes. Okay. Apart from these charges, okay, these holes and electrons, okay, these holes and electrons that you can see, these are charges which can move. Okay, they are known to be mobile in nature. They are known to be mobile in nature. Whereas on the p side, when you see, look at a negative sign with a circle, or if you look at the n side with a positive sign within a circle, then these represent immobile ions, as you have previously said correctly, that these are immobile ions. So there are three things that we have seen till now. One is the majority charge, other is the minority charge, third is the immobile ions. So these immobile ions, they are having a charge but they cannot move. Now if you come back to the question of that what is there at the depletion region, then if you look at the depletion region, then on the left hand side, that is on the p side, you can see that there is a column of negative ions. There are two columns of negative ions, and similarly on the right hand side you can see that there are two columns of positive ions. Okay. So what you can see here is that in this particular region, that is within these four columns, you don't find any negative charge or any hole. Okay, there is no negative charge, that is a electron, and there is no hole. So at the depletion region, you can find that there are positive ions on the n side, negative ions on the p side, but there are no mobile charges, that is the holes or the electrons within this region. And that's why this region is called as the depletion region. So the depletion region in a diode is the region at the junction, okay, because there is a connection between, there is a you may say there is a connection, okay, this,
P and diode.
yeah, there is a p, and between the p and the n regions there is a small thin line which is called as the junction. Okay, and within this junction, which has been magnified here, you don't find the junction to be so big within a diode, but it has been magnified here. So it's because it's in micrometers or something. So this junction, okay, it does not contain any mobile charges, whether it's a hole or an electron. And that's why this is named as a depletion region. Okay. Now, the purpose of this depletion region is that in the absence of any external voltage connection, I'm looking at the figure A itself. The purpose of this depletion region is that in the absence of any external voltage applied, none of the mobile charges either from the p side or from the n side can move into can cross the junction. Okay, so in the presence of this depletion region, none of the mobile charges, that is the holes on the p side which are majority, and the electrons on the n side which are the majority, they cannot cross the junction due to this depletion region. The reason is that if you look at the depletion region, then there is a positive charge on the right hand side and the negative charge on the left hand side. Okay? Positive charge on the n side, there are two columns of positive ions on the n side and two columns of negative ions on the p side. So what they do is they don't allow, there is going to be a barrier. When you look at this positive charge and the negative charge, then you say that there is a potential barrier existing there. So if there is a potential barrier, then this barrier is such that in the absence of any externally applied voltage, that is, it is written here, no bias condition, okay, no bias. In the absence of any external applied voltage, none of the charges, majority charges, can cross the junction. Okay, none of the charges can cross the junction in the presence of this potential barrier that exists due to the immobile ions that are present at the junction. So here there is another term that comes into the picture that is called as the bias. Okay, it is called as the bias. Bias. So what you have seen is, and I think all of you are aware also, that the symbol of a diode is like this. This is the symbol of a diode. The symbol of a diode. If you look at the previous figure that you had seen over here, then the left hand side is p side and the right hand side is n side. So in a diode, so this is called the p and this is called the n. This is called the, this terminal is called the anode. This terminal is called the cathode. The anode and the cathode. And what we have seen is that I am redrawing here. In this diode, yeah, you're not applying any external bias. So it's written there, no bias here. No bias. It means externally I am not applying any potential. So it's called a no bias condition. No bias condition. What is the meaning of bias? Bias means,
To favor something, prejudice.
yeah, bias means to not to be neutral. Okay, so you're either going to be on the good side or either you're going to be on the bad side, but you're not going to be neutral. Okay, that is called as the bias. Okay, somebody is in your favor or somebody is against you. That is a bias. So under no bias condition, so when I say no bias means there is nothing connected. So it's just a semiconductor diode present here. Okay, and there is no potential applied externally. So it is called as the no bias condition. But if we apply a certain potential DC voltage like this, then this is called as biasing. Biasing. Any potential. So you may connect in the reverse order also. Okay. You may connect in the reverse order also. You may take the negative terminal of the power supply and take the positive terminal of the power supply and connect it like this. I hope all of you are aware that the longer terminal is called the positive and the shorter one is called the negative of a DC supply. So this is positive, this is negative. Okay. So what you have done is that you started with a no bias condition, and you have seen that how does the diode look like in the absence of bias. So it looks like the figure A, that there is a P region, there is a N region, then there is a depletion region. Okay. And you also seen that there is a majority charge, there is a minority charge, and you've also seen what is the symbol of a diode. Now we are talking about biasing. The first kind of biasing is called the forward biasing, the forward biasing of a diode. In this biasing, what you do is you connect the positive terminal of the DC supply to the P region of the diode and the negative terminal of the power supply to the N region of the diode. The effect of the and this kind of a biasing where the positive of the power is connected to the P is called forward bias. Okay, this is called as forward biasing. The effect of this is that under forward bias condition, your depletion region, if you look at the depletion region, then its width is reducing. Initially, you saw that there were two columns of electrons on the P, or two columns of ions on the P side, and two columns of positive ions on the N side. Now, after doing the forward biasing, the depletion width has reduced. If you look at the depletion region, its width has reduced. And under this biasing, now the majority charges, that is the holes on the P side, can easily go into the N side, and the electrons on the N side can easily go into the P side. The electrons on the N side can easily go into the P side. So we are talking about the movement of the majority charges. The movement of the majority charges. So under forward bias condition, the holes which are a majority on the P side can easily go into the N side, and the electrons which are a majority on the N side can easily go into the P side under the forward bias condition. And the effect is to reduce the width of the depletion region. So if the width of the depletion region reduces, it means the potential barrier is also reducing. Now if you look at the reverse bias condition, the other case in which the P side of the diode is connected to the negative terminal of the power supply, and the N side is connected to the positive terminal of the power supply. In this case, as you can see, the depletion width has increased further as compared to the no bias condition. So the depletion width has increased further. So with the increase in the depletion width, your barrier has increased further. So in the presence of this increased barrier, the majority charges can no longer travel from their region into the other region. So no holes from the P side can go into the N side, and no electrons from the N side can go into the P side. But at the same time, this is assisting the flow of minority charges, that is the electrons on the P side and the holes on the N side. They can easily travel in the presence of this increased barrier. Okay. So the reverse bias actually assists the flow of minority charges. Okay, it assists the flow of minority charges. So if you look at this figure, then this kind of biasing is called forward biasing, and this is called reverse biasing. So this thing is also, you are all aware of it. Okay. So what we are saying is that if you look at the potential barrier, okay, potential barrier, the barrier is something like this. This is the barrier. This is called as the potential barrier under no bias condition. Okay, V naught is called the potential barrier under no bias, under no bias. Okay, this is what is happening. Now we're talking about a condition when you are forward biasing the diode. So when you're forward biasing the diode by a certain voltage, suppose you say that it is the voltage is D, VD, then on the forward bias condition, you are reducing this barrier by VD. So now your barrier is like this. So this part is V naught minus VD, V naught minus VD. This is the case of forward biasing, forward biasing. But in the case of a reverse biasing, if you apply the same potential VD, then this is actually adding up to your existing barrier. So it is like this. So now this is, okay, let me say this part is V naught plus VD. And this is for the reverse bias condition. This is for the reverse bias condition. Any questions here?
यस सर, ये जो ग्राफ हमने प्लॉट किया है वो किसके बीच में किया है?
किसके बीच में किया? On the x-axis is your distance, okay, and on the y-axis is your potential. On the x-axis is distance from the junction, distance from the junction, and on the y-axis is your potential. Okay. So what you see is that three cases come in front of you. One is when no biasing has been done. In that case also you see that if there is no biasing and you connect a ammeter to the diode, you don't find any current in that. Okay. You never find a current in a diode. When you hold a diode in your hand, you don't find a current in it. The current will only flow when you are applying a certain biasing, whether it's a forward biasing or whether it's a reverse biasing. So under forward biasing, what you do is you apply a certain potential. The potential is applied in this manner, PP, okay, PP. If the positive of the power supply is connected to the P side of the diode, or which is also known as the anode terminal of the diode, okay, that's called a forward biasing. But when it becomes PN, that is the positive is connected to the negative terminal of the supply, then it is called as the reverse biasing. And whatever potential you are applying under reverse biasing or under the forward biasing, that is directly added or subtracted from your contact potential. Initial potential, that is the potential barrier, also named as contact potential, As you see that under forward biasing, when I'm doing a forward biasing by VD, then the new barrier is V0 minus VD. Okay. Then the new barrier is V0 minus VD under forward bias. Now, how is it significant? Okay, so I am talking about this, I'm calling this as the junction. Okay, this is the junction. I call this as the N region, N part, and this I call this as the P part. On the P side, you are having holes, okay, holes, empty holes, empty energy bands, the holes. These can, these want to go into the N side, okay, so this P region, this is the right side is the N region, and when you are forward biasing, you see that when you are reducing the barrier, so you are actually, it's easy to cross this barrier when you have done the forward biasing. So it's easy for the majority charges, that is the holes on the P side, to cross this barrier when it is forward biased. But when it is reverse biased, this majority charges find it very difficult to, it's not possible for them to cross the junction. But at the same time, I said that under reverse biasing, under reverse bias condition, the minority charges, that is the holes on the N side, the holes which are a minority on the N side, they can cross the junction like this. It is as if you are sliding down from a higher potential. Okay, you're sliding down just like you do it in a slide. These charges, their polarity is such that this barrier is actually assisting their flow. It is assisting their flow, and that's why you find that under reverse biasing, also there is a current flowing through the diode, and that current is small in quantity. Okay, it's small in quantity, okay, but there is a current flowing. Now coming back to this forward biasing, any of the forward bias current, if you look at this polarity of the external supply, then the current must flow like this. Okay, according to the polarity, the current must flow like this. So this is the direction of the current flow of the diode under forward bias condition. IF, I will represent it by a subscript F. So this is the direction of the current flow under forward bias condition. And if you look at this, the other case, that is the reverse biasing, then in the reverse bias case, the direction of the current flow is like this. I will represent it by IR. Later on, we see that we use a certain symbol, we call the direction of the flow of the forward current as, we treat it as positive direction. And the direction of the flow of the current during reverse bias is treated as the negative direction. So later on, when we solve certain problems, this will be used over there, that a direction, whenever we solve a certain equation, we come up with a certain sign with the answer. So the sign is going to be sometimes negative or sometimes it is going to be positive. So by looking at the sign, we must be able to tell that whether the diode is forward biased or whether the diode is reverse biased. So the significance of the sign you can see over there, that why we are putting a sign to the flow of currents. So I'm again repeating, the direction of the flow of the current under forward biasing is designated a positive sign, and the direction of the flow of current in the reverse biased condition is treated as a negative sign. Okay, it is represented by a negative sign. So any questions here?